This is my fifth video about the best methods for converting acyl halides into ketones. Here I present some examples of how to acylate enamines with acyl halides. Enamines and enol ethers are synthetic equivalents of ketone enolates, but are significantly less reactive and basic. Enol ethers are neutral, but enamines are only slightly less basic than aliphatic amines. Enamines are basic and are protonated at carbon to yield iminium salts. Therefore, if one equivalent of enamine is mixed with one equivalent of acyl halide, only one half of the enamine is acylated at the beta carbon, while the other half deprotonates the product to the less basic enaminone. Therefore, either two equivalents of enamine are used, or an auxiliary base, such as triethylamine, is required to attain complete conversion of the acyl halide. Enaminones are vinylogous amides and much more stable toward hydrolysis than the starting enamine. Thus, to obtain the 1,3-diketone, sometimes quite vigorous conditions are required for their hydrolysis, such as refluxing hydrochloric acid. Care must be taken not to destroy the target diketone, which can sometimes be rather unstable. If an excess of acyl halide is used, sometimes the enaminones are acylated at oxygen, and careful hydrolysis can yield enol esters of 1,3-diketones. More vigorous hydrolysis conditions will, however, again yield the unacylated 1,3-diketone. The acylation of enaminones at carbon has also been reported, and it is therefore advisable not to use an excess of acyl halide in these reactions. Acyl halides with alpha hydrogen will be converted to ketenes by bases such as triethylamine or most enamines. In such instances, cyclobutanones may be formed as intermediates, which however are not very stable and can undergo ring fission to the expected enaminone. Enamine chemistry was investigated thoroughly in the 50s and 60s, and it seems that morpholine-derived enamines usually give best results. Morpholine is less basic and more resistant to oxidation than other secondary amines, what could be the reason for the advantages of morpholine-derived enamines. The auxiliary base must be at least as basic as the starting enamine to prevent iminium salt formation. Triethylamine seems to be a good choice, while pyridine is not basic enough. It has also been observed that highest yields are usually obtained when no precipitates form during the reaction, and chloroform seems to be a suitable solvent, despite its sensitivity toward bases and amines. Solutions of amines or enamines in chloroform shouldn't be kept for more than 24 hours, because this can cause the formation of a whole new set of byproducts. The main advantages of the enamine strategy, if compared to lithium enolate chemistry, are that most starting materials and reagents are inexpensive and readily available, and that neither strong bases nor anhydrous solvents are required. Enaminones are also acylated much more slowly than the starting enamine, and it is usually no problem to perform clean monoacylations. One problem of this chemistry is the requirement of a secondary amine as auxiliary, and that the enamines usually have to be isolated and purified. Yields of enaminones or diketones are often low, and ketones containing base-sensitive groups, such as leaving groups for nucleophilic displacement, epoxides, or reactive esters or lactones, cannot be readily converted into enamines. Moreover, enamines cannot be stored indefinitely and tend to oligomerize or to be oxidized by air. Before LDA and similar bases became readily available, enamines were valuable synthetic intermediates. But today, enamines are only rarely used in synthesis. Usually, it is easier to generate lithium enolates in situ, either from a ketone or an imine. Lithium enolates are more reactive than neutral enamines and usually react much faster. This is an example of an optimized enamine preparation and acylation. All the steps, including the hydrolysis of the intermediate enaminone, proceeded in high yield, despite the fact that ketenes were probably also formed as intermediates. This newer example is actually the acylation of a ketene aminal, that is, of an amide enolate equivalent. Despite the electron withdrawing effect of the fluorine atoms, the CC double bond was still nucleophilic enough to react with propionyl chloride without the need of any catalyst. It is maybe worth mentioning that the resulting ketoamide must be very sensitive toward nucleophiles, because the difluoroacetamide anion is a good leaving group and because nucleophiles may also attack the fluorine atoms and the product may act as electrophilic fluorinating reagent. In this example, a rather unreactive enamine was acylated with the highly reactive oxalyl chloride. The starting enamine is similarly unreactive and sparsely basic as the enaminones obtained by acylating normal enamines. Oxalyl chloride, however, is exceedingly electrophilic and a good hydride abstractor as well. And since only one equivalent of oxalyl chloride was used, the final oxidation was probably caused by air. As already mentioned, and as shown by the last example, enaminones can be acylated both at carbon and at oxygen, what would consume one additional equivalent of acyl halide. The oxygen-acylated enaminones are, however, still potent acylating reagents that could still be able to acylate the starting enamine. If ketene formation leads to cyclobutanones, these may yield two different products upon ring cleavage. Thus, intermediate ketene formation can lead to unexpected isomers. One further potential problem is the reaction of the enamine as electrophile. Because enamines are protonated at carbon, yielding iminium salts, these may react with the starting enamine to yield Mannich-type products or with other nucleophiles present in the reaction mixture. Enolates of acyl halides usually split into ketenes very quickly, but ketenes are nucleophilic at the beta carbon and can be used as ester enolate equivalents. Less strongly activated carboxylic acid derivatives, such as the imidazolide of this example, may yield, upon treatment with enamines, enolates capable of adding to iminium salts. The reaction of this slide can probably be suppressed by an excess of a tertiary amine, which would prevent the formation of an iminium salt. On this slide there are some further examples and recent reviews about the use of secondary amines as organocatalysts. The in situ formation of enamines and iminium salts has become a hot topic, in particular its application to the enantioselective synthesis of various products with the aid of only catalytic amounts of enantiomerically pure secondary amines, often derivatives of some alpha amino acid.